Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. In this video, I would like to discuss about second order differential equations. So these are the things that we are going to discuss. I will start with the introduction and then linear homogeneous equations. These are the objectives in this chapter. Okay, I hope everybody can determine the solution of homogeneous second order differential equations with constant coefficient. Second objective, everybody must know how to solve non-homogeneous equations by using the method of undetermined coefficients. And last but not least, okay, everybody must know how to apply the second order linear differential equations in solving engineering problems. So, for introduction, a linear second order differential equation can be written as a d square y dx square plus b dy dx plus cy equal to fx, where a, b, and c are constant coefficients while fx is a given function of x. There are two types of linear second order differential equations. The first one, homogeneous differential equation. Why homogeneous? Okay, our fx is equal to 0. Second type, non-homogeneous differential equation, where our fx not equal to 0. In previous chapter about first order differential equation is not enough to solve many engineering problems. Most engineering problems use second order differential equation to find the solution. So here are the example of application of second order differential equation. The first example, second order differential equation can solve electric circuit. So here is the equation. Then in mechanical system, the equation solved to use Hooke's law is second order differential equation 2. And the next example that use second order differential equation to solve the solution, to solve the problem is a deflected beam. Now let's discuss how to solve for linear homogeneous equations. The second order differential equations are said to be linear homogeneous if our fx is equal to 0. So our equation becomes a d square y dx square plus b dy dx plus cy equal to 0. How to solve this homogeneous equation? So firstly, we let y is equal to exponent lambda x. Then we differentiate this equation twice. Differentiate for the first time, we will have dy dx is equal to lambda exponent lambda x. And we differentiate for the second time, we will have d square y dx square equal to lambda square exponent lambda x. After that, we substitute these three equations into our equation number 1. So we obtain a lambda square exponent lambda x plus b lambda exponent lambda x plus c exponent lambda x is equal to 0. Then we factorize the exponent lambda x and we simplify. So this is our final equation. The equation we obtained earlier, known as an auxiliary equation or characteristic equation. Since the characteristic equation is a quadratic equation, so we need to find the roots of the equation. So, how to find the roots of quadratic equation? So, firstly, you can factorize. Second, you can use completing the square. Or the third one, you can use formula. So, this is the formula how to find the roots of equation. Actually, right now, you can directly use your calculator to find the roots of quadratic equation. After you have the roots of the equation, so you need to identify the roots belongs with cases. So there are three cases of roots. The first one, we have different roots, or roots 1 is not equal to roots number 2. So the general solution is y is equal to c1 exponent lambda 1x plus c2 exponent lambda 2x. Second cases, if roots number 1 is equal to roots number 2, that means we have equal roots. Then our general solution is y equal to c1 exponent lambda 1x plus c2x exponent lambda 1x, or we can simplify it by we factorize exponent lambda 1x. And the last cases, if you have a complex root means your lambda is equal to alpha plus minus beta I. Hence, our general solution is y equal to c1 exponent alpha x cos beta x plus c2 exponent alpha x sin beta x, or we can simply simplify it by factorize exponent alpha x. For better understanding, let's try one example. So this example, we need to solve equation number 1 and equation number 2, where both of the equation is a homogeneous equation since this is equal to 0. So number 1, our equation y double prime minus y prime minus 2y equal to 0. So let's transform the equation into our characteristic equation. Y double prime is equal to lambda square. Y prime is equal to lambda to the power of 1 minus 2y is equal to lambda to the power of 0, that is equal to 1. So equal to 0. So now we have our characteristic equation, that is a quadratic equation. So how to solve the quadratic equation? So we just need to factorize the equation. So factorize the equation, we will have lambda minus 2, lambda plus 1 is equal to 0. So from here, we have lambda 1 is equal to 2, while lambda 2 is equal to minus 1. From here, we have different roots. So based on the table, the general solution for different roots is equal to y equal to c1 exponent 2x plus c2 exponent minus x. Okay. Now let's move to the number 2. So our equation is y double prime minus 7y prime equal to 0. So let's transform into our characteristic equation. Y double prime is lambda square minus 7y prime is lambda to the power of 1 equal to 0. So we factorize this characteristic equation. We have lambda minus 7 equal to 0. So lambda 1 is equal to 0 while lambda 2 is equal to 7. From here, we have two different roots. So the general solution for two different roots is y equal to c1 exponent 0x plus c2 exponent 7x. And we simplify c1 plus c2 exponent 7x. So now, example 2. Let's solve these two equations. Okay, so we start with equation number 1. So we have y double prime minus 8y prime plus 16y equal to 0. So we change the equation into our characteristic equation. So we will have lambda square minus 8 lambda plus 16 equal to 0. So now we factorize our quadratic equation. So we will have lambda minus 4 to the power of 2 equal to 0. So from here, we have two equal roots. Lambda 1 is equal to lambda 2 is equal to 4. Since we have two equal roots, then our general solution is y equal to e for x bracket c1 plus c2x. Solution. That is the solution for equation number 1. So now let's move to the second equation. Okay, second equation we have y double prime is equal to 0. Okay, so our characteristic equation is lambda square is equal to 0. So we factorize this one, we will have lambda 1 equal to lambda 2 is equal to 0. So this equation also we obtain equal roots. Then our general solution become y equal to e0x bracket c1 plus c2x. And since exponent 0 is equal to 1, so our general solution is c1 plus c2x. So now let's move to the next example. So equation number 1. Okay, so we have y double prime plus 4y prime plus 4y equal to 0. Then we change into our characteristic equation. So we will have lambda square plus 4 lambda plus 5 equal to 0. Now let's find roots of this equation. So our root is equal to lambda equal to minus 2 plus minus I. That means we have a complex roots. So from here, we have alpha is equal to minus 2, while our beta is equal to 1. Since we have complex root, so the general solution for complex root is equal to y equal to exponent minus 2x bracket c1 cos beta x, so cos 1x plus c2 sine beta x, so beta is equal to 1x. For equation number 2, okay, so our equation is y double prime plus 4y equal to 0. Our characteristic equation lambda square plus 4 equal to 0. So from here, we have our roots. Lambda is equal to plus minus 2i. So from here, our alpha is equal to 0, while beta is equal to 2. So this is a complex root. So the general solution for complex root y is equal to exponent 0x, c1 cos 2x plus c2 sine 2x. Simplify, we know exponent 0 is equal to 1, so y is equal to c1 cos 2x plus c2 sine 2x. In this example, we are going to find the particular solution of this equation. We are given to us two initial conditions. So let's start the calculation. Our equation y double prime minus 4y prime plus 13y equal to 0. Our characteristic equation lambda square minus 4 lambda plus 13 equal to 0. We factorize the equation. We have lambda is equal to 2 plus minus 3i. That means we have a complex root where alpha is equal to 2 and beta equal to 3. The general solution for complex root y equal to exponent 2x bracket c1 cos 3x plus c2 sine 3x. So this is our general solution. Now we are going to find the particular solution. Firstly, let's use the first initial condition y0 equal to 1. Substitute into our general solution. We will have E0, C1 cos 0 plus C2 sin 0 equal to 1. So from here, we know exponent 0, 1, cos 0, 1, sin 0, 0. So we have C1 equal to 1. Then our equation y equal to e to x. Since C1 equal to 1, so we have cos 3x plus C2 sin 3x. Now, we are going to find the value for C2. That means we are going to use the second initial condition. Y prime 0 is equal to 2. Here we see we have prime here. That means we need to differentiate our equation. So we differentiate by using product rule. We will have y prime equal to 2e to x cos 3x plus C2 sin 3x plus e to x bracket minus 3 sin 3x plus 3C2 cos 3x. Now we can substitute the second initial condition, give us 2 exponent 0 cos 0 plus C2 sin 0 plus E0 minus 3 sin 0 plus 3C2 cos 0 is equal to 2. Let's simplify. We know exponent 0, 1, cos 0, 1, sin 0, 0, exponent 0, 1, sin 0, 0, cos 0, 1. So, we have C2 is equal to 0. Then, our particular solution is y is equal to exponent 2x. C1 is equal to 1, so cos 3x. And C2 is equal to 0. So this is the particular solution. Now let's try one example of application. A spring with a mass of 2 kg has natural length 0.5 meter. A force of 25.6 Newton is required to maintain it stretched to a length of 0.7 meter. If the spring is stretched to a length of 0.7 meter and then released with initial velocity 0, find the position of the mass at any time t. Given to us, the vibrating spring equation is md square x dt square plus kx is equal to 0. So now let's start the calculation. We have mass equal to 2 kilo. And then we have natural length, we have 0.5 meter. From here, we can calculate restoring force. Okay, so restoring force, how to calculate? We have Kx is equal to 25.6. K, X is equal to 0.7 minus 0.5 equal to 25.6. We rearrange, we have K is equal to 128. We substitute into our differential equation. We have 2d square x dt square plus 128x equal to 0. So now let's change into our characteristic equation. We will have lambda square 2 lambda square plus 128 is equal to 0. We factorize the equation. We will have complex root where lambda is equal to plus minus 8i. Since alpha equal to 0 and beta is equal to 8. So our general solution is C1 cos 8x plus C2 sin 8x. Oh, sorry, this is not y, this is x. And this is t. Okay. So now let's find the particular solution. The first initial condition we have, x0 is equal to 0.2. So we substitute into our equation. C1 cos 0 plus C2 sine 0 is equal to 0.2, given to us C1 is equal to 0.2. So our equation x is equal to 0.2 cos 8t plus C2 sine 8t. Second initial condition, we have x prime 0 is equal to 0. Okay, we can see we have prime here. That means we need to differentiate our equation. So differentiate the equation, we have dx over dt is equal to 8 times 0.2 minus 1.6 minus 1.6 sine 8t plus 8c2 cos 8t. Substitute the initial condition we have. So minus 1.6 sine 0 plus 8c2 cos 0 is equal to 0. Given to us c2 is equal to 0. Then our particular solution is x is equal to 0.2 cos 8t. I hope everybody can understand about introduction of second order differential equation and how to solve homogeneous linear differential equation. See you in the next video on how to solve the non-homogeneous linear differential equation. Thank you.